Okay guys, let's take a look at independent practice for 6.4. They want us to determine whether or not the two quantities shown on each table or graph represent a linear relationship. If so, find the constant rate of change. All right, let's just take a look at 1. So they give us 4x. Right, so we have 5, 8, 12, 24. So we're going up by 3, by 4, by 12. So we don't have consistency right there. So it's going to be a little bit of a challenge. And for our y's, we're going from 15 to 24, an increase in 9. We go from 24 to 36, an increase of 12. And we go from 36 to 72. All right, so what do we have right here? So if we go up 3, and our y, we're going up 9. Right, so let's take a look at that. So from 5 to 8 and 15 and 24, it's 9 over 3. From 8 to 12, right, we're going up 4. From 24 to 36, we go up 12. So 3, 3, and then here we go up 12, 36. So 36 divided by 12 is 3. So guys, it certainly looks like we do have a linear relationship, and our constant rate of change, which is our slope, is 3. Okay, what about 2? Distance traveled by a falling object. Okay, so distance traveled by a falling object. So here we have 4.9, and the 1, 2, 3, 4 is time in seconds. Okay, then we have 19.6, 44.1, 78.4. I mean, come on, guys. Okay, so that's 14.7 as we go up 1. So here we go up 1 from 2 to 3, and we're changing by, what is that? 24.5. Right? And then right here from 3 to 4, we go up 1, and we're changing right here by 34.3. So we have no consistency. So that's not a constant rate of change we're looking at. Right? Because x's are changed by the same amount each time, the y's are not. We go from 14.7, 24.5 rather, to 34.3. So it's not linear. All right, what about 3? We're talking about oil and vinegar, Italian dressing recipe. All right, so Italian dressing recipe. I'm going to put oil, I'm going to put some vinegar in there. So oil, we're talking cups. We're talking 2, 4, 6, or 8 cups of oil. Now, what are we getting with the vinegar in cups? So we get 3/4 of a cup, 1.5 cups, 2 1/4 cups, 3 cups. Well, goodness. I'm going to go ahead and I'm going to do decimal conversions. Right, so 1.5, 1.5, 2.25. I'm going to drop that. So the reason why I do this is it just makes it easier for me to see if things look like they're changing at a constant rate. Right, so from 2 to 4, I'm adding 2. I'm going from 0.75 to 1.5, adding 0.75. 4 to 6, going up by 2, going up by 0.75 plus 2. 6 to 8, we're going up 2, and here we're going up 0.75. Now keep in mind though, right, if you tell me that the rate of change is 3/4 of a cup per cup of oil, you're wrong, because it's 0.75 over 2, right? So at this point, I'm not going to go to my calculator, guys. I'm going to do old school math and magic. So 0.75 is really 3/4, right? So what I'm going to do here is I'm going to change division to multiplication, and I'm going to flip this. So our slope, or our rate of change, our, in this case, constant rate of change, all right, is 3/8 of a cup of vinegar for every 1 cup of oil. That's our constant rate of change. All right, now 4, 5, and 6, same idea, but they're giving us graphs now. All right, so it certainly looks in 4 like we have a linear relationship, right? Because we have 0, 0, 1, 1, I'm sorry, 1, 2, rather. So 1, 2. So 0, 0, 1, 2, 2, 4, 3, 6. So every time we're increasing by 1, our output values increase by 2. So this is good, and our constant rate of change, right? So the rate of change, or our slope, which is constant, is going to be 2. 2 what? It's going to be 2 inches per minute that the water level is changing. It's our constant rate of change. All right, and what about 5? Possibly, right? So we have some dots that look like this could possibly work for us. So what do those things represent? So we're talking about map distance, right, in inches, 2, 4, and 6. And then we're talking about our output is aerial distance in miles. So it looks like our scale is 15 per box. So we have 215, 430. Now, if this is linear, we would expect this, right, to have a constant rate of change of 15, right, as we're going up 2 and up 2. If this is 15, we'd expect this to be 45, and it actually is 45. All right, fantastic. So every time we go up 2 on the x-axis, we're increasing by 15 on the y. So it certainly looks like our rate of change is constant, but it's not 15 over 2, guys. 7.5. Now 7.5 what? 7.5 miles per inch, because we're looking at a scale. And that's going to be constant, all right, because 15 over 2 is going to give us the same thing. It's going to yield the same answer as 30 over 4, 7.5, and 45 over 6, 7.5. So we have a constant rate of change right there, right? Now, what about 6? We're looking at people and total cost, right? Total cost versus people. Try to make this legible for you. Make this a little more legible. Total cost and people. So it certainly looks like we have right here 5 100. Then we have 10 and 15. So 10, we come up to, looks like 175. And then at 15, it looks like we go up to 250. So 5 100, 10 175, 15 250. So my x's right here are increasing by 5. What happens to the y's? Up by 75, up by 75. So that looks like we're being consistent right there, right? So every time x changes by 5, y changes by 75. So it looks like we have a rate of change that is certainly going to be constant. All right, now let's see what that is, because it's not 75, right? It's 75 over 5. All right, so our constant rate of change is going to be $15 per person. So $15 for every 1 person. All right, now 7, 8, 9 are interesting. All right, so 7, 8, 9, does a proportional relationship exist between the quantities shown in the following exercises? So exercise 7 says, let's go back to 1. All right, let's go back to the 5, 8, 12. Here we go. Here we go. So let's go back to the 5, 8, 12, 24, and let's see, is this proportional? All right, so we have 15 over 5, which is 3. 24 over 8, 3. 36 over 12, 3. 72 over 24, 3. 3, 3, 3, 3. So, yes. So number 7, is it proportional? Yes. I explain our reasoning because when we sit there and do B over A, every time we go to a new B over A, the change in B over change in A, right, that's constant. All right. So let's go ahead and let's flip to the next page. All right, so let's see here. What do we have on the next page for independent practice? We have match the table with its rate of change. All right, because number 8, we go to exercise 3, and we saw the yes, that 0.75 was consistent. So this, once again, this is a yes. It's 0.75 every 2, so that's a yes, it's proportional. And then for number 9, we're looking at exercise 5. We're looking at the map and that distance. All right, so everything here, once again, so we have that constant rate of change. So change in B over change in A, 7.5 miles per inch. And then we do 15 over 2, 30 over 4, 45 over 6. We get 7.5, 7.5, 7.5. Right, so 9 is a yes as well. Right, so match the table on 10 with its rate of change. Okay, so 20, 30, 40. And we're doing 170, 162, 154. 71, 62, 154. So what's happening here is every time y decreases by 8, x increases by 10. So that's negative 4/5. And what that corresponds to, because we don't have a negative 4/5, but they do give us negative 0.8 feet per minute. So negative 4/5 is negative 0.8. Boom, right there. Okay, what about this one? Right, time and distance. So this one we have 1, 2, 3, 20, 30, 40. So our y's are going up 10 every time x goes up 1. So we look over there to the left, and sure enough, we see 10 feet per minute. Boom. Okay, third one. So we have 4, 6, 8, 1, 1.5, and 2. So our y's are going up 1/2 every time our x's go up by 2. All right, so what's happening is keep, change, flip. Right, so it certainly looks like 1/4. All right, so 1/4 is going to be our rate of change or our slope. And once again, they don't give us 1/4, but they do give us 1/4 as a decimal. You simply have to recognize that. So 25/100ths feet per minute. And therefore, by process of elimination, right, so we have 5, 10, 15, 12, 24, 36. Right, so every time y is going up by 12, x is going up by 5. So that is going to be 2.4 feet per minute. Boom. Okay, harder thinking problems. Ooh, a dog starts walking, slows down, and then sits down to rest. Sketch a graph of the situation, represent the different rates of change. Label the x-axis time and the y-axis distance. Well, that is a challenge there, guys. So dog starts walking. So I can say dog's going to start walking at kind of a consistent pace. It's going to look like a line. Then the dog is going to slow down. So he starts walking at a constant pace. He's going to slow down. So we have a curve. It's going to curve. And then if he sits down to rest, all right, he sits down to rest, then, so we're looking at time. So his distance is not changing as he's resting. So time is going to be x, because our distance along the y-axis depends upon the time the dog's been walking. Right, so we need some kind of a stiff line right there. You can make it as as steep or as narrow as you'd like. Um, then we need some kind of a curve because we're slowing down. And then we just need kind of a flat line where the dog is stopped. All right, number 12. Describe a situation with two quantities that have a proportional linear relationship. All right, well, something right there. I mean, easy for us, right? You all do athletic participation, so maybe set number 1 you do 12 reps, set number 2 you do 10, set number 3 you do 8 reps, set number 4 you do 6 reps. So every time, right, our slope is -2, -2, -2. Um, but here's the thing, though. We're talking about proportional, though, guys. So we have to look at our B over A. So 12 over 1, 10 over 2, 8 over 3, 6 over 4. That's where it falls apart. All right. So this is linear, but it's not a proportional linear relationship. Ooh. So guess what that means? You get to make up your own story. Do it now. All right. So you made up your own story to fit that description, right? Two quantities have a proportional linear relationship. And that takes us into the last one for independent practice. We're looking at lucky number 13. Take us to the school player 250 each. Which table contains values fit the situation if C represents total cost for T tickets? Well, in that case, okay, so total cost for T tickets, right? So T tickets is really X, and total cost, right, it's really our Y. So, right, something like a 1, 2, 3, 4, and if the cost is $2.50 a ticket, then 2 tickets should be $5, 3 should be $7.50, 4 should be $10. All right, now, geez, A is out because you're only increasing by 75 cents each time you go up by 1. So if tickets are $2.50 each, if you buy 2 tickets, you're not going up by 75 cents, guys, right? You're going up by $2.50. So A is out of there. What about B? So we start out at $3.50 and then go to 6, $8.50, and 11. So B is very tempting because $3.50 to 6, 6 to $8.50, and $8.50 to 11. Well, it's all going up by $2.50. The problem is, guys, the first ticket should be $2.50 and not $3.50. So B's out of there. So now we're down to a 50-50 shot, and C's out because start off at $3.50. Boom. That's ridiculous. So it has to be D by process of elimination. Right? If you want to make yourself feel better, go ahead and look at it. Right here we have $2.50, $5, $7.50, and 10. Exactly what we would expect if tickets are $2.50 a piece, and we bought 1, then 2, then 3, then 4. All right, that's independent practice.